All right, welcome everyone. Thanks for coming today. I know some people are off at conferences, but I appreciate you here, and I think we have a really interesting talk. So today's speaker is Anthony Tomasic. He is a longtime Carnegie Mellon professor, currently CEO of Fort Alto. So he's that's his primary line, but he's still a consultant at the Robotics Institute here at Carnegie Mellon. So he was just a senior system scientist, I guess.
That's what I was, not a professor.
It's well, it is a kind of professor, right? It's in the hierarchy somewhere. So I mostly understand these things after 20 years, but so he co-founded and directed the Master of Computational Data Science degree program, which is definitely going strong, a big part of our master's curriculum. He also co-founded the Master of Science and Product Management.
Yay!
He received the Alan Newell Award for Research Excellence as part of the Tiramisu Transit Project in 2021. So if you've ever used the Tiramisu app to figure out when your bus is coming.
It's dead now, by the way. We
It's
finally
dead.
killed it off, but it was running for 10 years.
Okay.
Yeah.
So Anthony received his undergraduate degree in computer science from Indiana University, a PhD in computer science from Princeton, and an MBA from CMU. Today he'll talk about using AI and software architecture ideas to do application manufacturing.
Great. Thank you very much. Thanks. It's always good to come back to Carnegie Mellon. It's great to see familiar faces. It's a real pleasure. So I'm going to talk to you today about a new way to build applications. And the origin story for this company is about 4 years ago, I started working with Anna Florescu, my co-founder, and she was a consultant for a hydroponics company. So this is people who take a warehouse-sized building, fill it full of plants that grow in liquid, and then they harvest them repeatedly and sell them. And they were building an Internet of Things infrastructure on top of that. It's very complicated. You have reserve tanks of different kinds of fluids. You have pumps. You have drainage. You're controlling light, power. You have solar energy in addition to regular power. You have to worry about the chemical compositions of what you're doing, et cetera. So it's a relatively sophisticated Internet of Things application. They put together their entire infrastructure once in year one, realized they had done it wrong, tore it apart. Then they did the whole thing again in year two, realized again they had done it wrong, tore it apart, and did it again in year three. And it turns out in the Internet of Things community, this is actually not that unusual. And so we thought that this was really stupid. And so we sort of reverse engineered what they were doing and tried to figure out a better way of doing it. And that's what I'm here to talk to you about. So just to summarize the area that we're looking at, or the problem we're looking at, is that when you're building applications these days, they're hard to build. Actually, modern applications are really built by tying together lots of different pre-existing components, and then you sort of inject a little bit of your own code to do whatever you want. And the target is always the same thing, this sort of gigantic brick of code. And that resulting brick is sort of well understood to be hard to understand. You can execute it, but you don't really treat it as an analytical object itself. It's hard to understand what's going on. In particular, the first implementation of an application is only 10% of the cost compared to the total cost of ownership of an application over time. And every time you change that application, there are hidden dependencies that are sitting around the brains of developers. And so it's always a risky thing to do. And this problem is made worse these days. It's probably what everybody in this room these days is doing, is building AI pipelines. So, keeping track of the various pieces of your application and what it's doing is a hard thing to do. This diagram I stole from a paper by Mary Shaw. She's actually writing about the same idea, but from a different perspective. Her perspective is from architecture and programming languages. But the point of this paper, which is a beautiful one, is that programming languages are really doing a lot more than what you get in an introductory programming class of the actual code. And this is actually a piece of work that she references and shows up in her paper, is done elsewhere. Each one of those nodes represents a component, and then you go off and survey a bunch of actual applications, and you can populate the strengths between these various components here. So the detail of this slide isn't that important. All I'm saying is that modern applications are constructed by putting together a bunch of components in a bottom-up way. So it's actually sort of an artisanal craft that all developers are really doing these days. So I'm a big fan of large language models. In fact, you'll see them applied later on, but I really like the image stuff that they're doing now. So I thought to make if you don't have any other point that you get out of this entire talk, the one point that I want to make is that applications today intertwine the functionality of the application with infrastructure code. So for fun, and being inspired by Andy Pavlov's Gonzo stuff in the classroom, I thought I would ask an image generator to tell me what this actually looks like. And this is what it ended up giving me, which I thought was a lovely representation of the problem. So that is the main point. This is our hypothesis is that this is a central problem in making applications, and that our solution is at least one way of cracking this particular application. All right, so that's the introduction, and this is the main structure of the talk. When we reverse engineered things, we actually took a database perspective, and what that does is it allows you to split up the problem of a generic application into three pieces. The first piece is you have some kind of application model. And so when you start developing your application, some stakeholder, not necessarily developer, is going to instantiate that application model. The majority of this talk is actually going to be on this first point here, because to actually walk through the mechanics of that with an example is going to take me another 15, 20 minutes. And what you do then is the autocoder tool, which is what our company is developing, can automatically generate the application. And when I mean the application, we have a very technical definition. It is this application semantics graph, and you'll see an example of that. Given one of these graphs, you need a little bit more information to understand what the infrastructure looks like. And once you populate our infrastructure model, autocoder can automatically generate the build and install deployment scripts for that application, send them to the appropriate components, start the application running. Okay? So the developer actually doesn't have to do this work. Today, it's exactly the mix of 1 and 2 that causes applications to be so brittle and difficult to develop or manipulate. All right? And then finally, once you have a running application, but you've split it into these two pieces, you can actually do formal changes to your application in a controlled way. You can say, I want to add a new piece of data flow here. I want to change the code here. I want to replace some instances. And we can formally generate the code and execute the code that requires you to make that makes that required change. Today, in any large-scale application, this is cooked up by the infrastructure development teams. Okay, this stuff is done bespoke for every single company, and there are even companies that specialize in producing tools that allow you to do this. That's infrastructure as a code. There's a whole market there for doing this kind of work. We can just leverage all that work to do this these kinds of modifications. I'm going to spend very little time on this, but actually this is where all the juice is, because now you're impacting this total cost of ownership as opposed to just time to market of the initial application. Okay. All right. So I said that we used a database perspective for this. I'm just going to take a few seconds to talk about relational databases here. If you squint and you look only inside of the database, the application part, the formal semantic part of the application, really consists of the schema, some queries and transactions on top of them, and the user-defined functions. The infrastructure of an underlying database is its runtime system, the imposition of ACID properties, the reliability and security you get with any operations you do inside of the database. It takes care of communication and parallelization because it's doing, again, this automatic program generation. You get location transparency. A lot of these properties that I was just saying that I claimed in the previous slide that you can do. So there are worlds in computer science already which have the kinds of properties that we're talking about. Okay, and I'll come back to this point in a minute. Okay, so again, just to tell you, we're here at step number 1, and I'm going to give you the details of that. So we need a model for the underlying application. It's broken up into these pieces. There's going to be an entity hierarchy that has instances associated with it. There's going to be an operator library with a bunch of code. And then there's going to be these task data flows. All of that is stuffed into our tool, and then it generates this conceptual graph of an actual application. You don't need to read this. I'll blow it all up in steps. Okay, so the first part is we want to describe an environment where the application is actually operating. We are using for that at the moment an entity tree which has relationships. So it's not an is-a type hierarchy, it's a has-a. And the application that I'm going to show you is a very simple one. Obviously, the underlying system extends to millions of instances and entity classes. But for the example I'm actually going to run, it's got to be simple enough to explain. And the application is, we have cameras attached to doors. Doors are in rooms, attached to rooms, and they're inside of a building. And those cameras are taking pictures all the time, and those are stuffed into a data processing pipeline, which first crops the faces out of those images, takes each face and does image recognition on it. If the recognition is successful, you get a business key. And then we can go look up that business key in a database to populate additional information about recognized faces. And then, of course, you have the unrecognized faces. And all of that gets dumped to a monitor. Okay? So here's, for our toy example, the instances that we have. Since it has a hierarchy, we get these path expressions that are automatically part of the model. And we've got a single building that has 2 rooms and 3 doors. And you'll see we'll have a camera attached to each one of those doors. Okay, so I have the abstract schema. I've populated that schema with instances, the entity schema. You can think of the left hand here, my left hand here being this entity schema. On the right hand, I've got an operator library. And those are all of the underlying actions that the application can take that have been split up into very small components. So this is a typical component library. For my particular example that I'm talking about, I need 6 of these. I need some kind of heartbeat. That's just a simple operator that sends a signal at a certain amount periodically. That triggers a camera. So now I have a stream of heartbeats going into cameras. The cameras, every time they get a heartbeat, read their sensors to generate an image. So I get a stream of images coming out. Each one of those images is stuck into a computer vision model that crops out the faces. So an individual image might generate multiple faces. And then I run face recognition on each one of those. The ones that give me a business key, I can send to a database through this enrich operator, and then I dump everything to the monitor. And it's a 4S because some of these classes have subclasses. There's a bunch of detail here I'm not going to talk about. There's a whole type system here that I'm not going to talk about. The important thing to remember is that I've got a bunch of these very simple components. All of these actually you can get off the shelf, right? You could get them from a component marketplace. Or you could, in fact, do exactly what we did, which was simply steal them from GitHub. And then we provide a bunch of other services. So we find in IoT systems, a lot of the code actually simply reduces to automata. So we give you an automata, you give us a little bit of data about how the automata works. We can automatically generate dashboards. We'll show that later. Logging, of course, you can plug into the system. And we also provide a complete controller system for the underlying instances. You can do data generation. This turns out to be important later on. Okay, so you've got all the entities and all the operators. And I'll give you a little more detail about the operators just to understand the example. Here's a particular operator. It uses the OpenCV camera library that runs on Pies or elsewhere. And then we use a port system where you can define these input ports to the operator and you have output ports. So it's sort of a data flow streaming model. These can be asynchronous, in which case the messages are simply flowing through a data flow, but they can also be synchronous, which is the same thing as an RPC call, or in the right combination, we could do futures. So that's the definition of the external interface to the operator. There's some Python code. We have to declare the requirements. You'll see later on how this actually works. And then you could parameterize any particular instance or task or operator in the system. Because you might have different cameras at different doors. You want to parameterize what they're doing. And then we have some other stuff that we have on the end here. I'll just give one example. You might want to indicate that this particular operator can't be moved. It turns out, because we have an abstract description of the application, we can move code anywhere we want through the infrastructure. Obviously, this code is stuck at a particular place in the infrastructure. You don't want the optimizer saying, oh, it's more efficient to move the camera into the cloud. Okay, now I'm going to break a rule of talks. You're never supposed to show code or this much code. But I really wanted to do this because I wanted to show how simple each one of these components is. In fact, this component can be generated by just using GitHub Copilot and just typing in a particular definition. The linkage to the rest of the system is by making this class a subclass. At the top there it says Auto Camera OpenCV. That's an automatically generated superclass that contains all the guts that you need to take an instance of this class and integrate it into the rest of the system. Then you have an initialization operator, and then at some point in time after the object is initialized, it receives an initialize resource message, which is typically a function call, and it'll set up its internal state. And then again, the time passes, and then finally a heartbeat message shows up from that heartbeat operator that I mentioned, and it will call the camera, read whatever the sensors are saying, construct an image with a flag here. The flag tells you if the image is good or not. And then remember the output port, that gives you automatically this method, which again is in your superclass, that allows you to send a message out. And then there's this data conversion that has to happen because this is sort of some internal arbitrary state that has to be converted into something that can go over our transmission, our communication boundary. So you get this automatically from the underlying class. I admit here this line is a hack. I cheat a little bit for error management. It turns out error management in these systems to reduce the amount of code that you have to write to do all the exceptions is still a little bit of an open problem. we have a solution for this, but here I'm just going to dump something to a file. And then finally, at some point in time, you might want to tear down this object, but before you do that, you want to be able to release your resources, so this object will get a message saying, I'm about ready to kill you off, you better release whatever resources you have. And that's it. Okay, that's the entire sensor code. It's less than a page. And clearly something that can be easily generated by Copilot or Devin or any one of these, there's a huge arms race going on now to do code generators. All right. So you've seen the trees, you've seen the instances, you know what the signature of the operator library is, you have an example. Now I have to connect together these two separate chunks. And we're going to do that by declaring a task, giving it a name, an entity in the entity tree, and an operator. Okay, so in particular, we'll say there's a camera task, it's attached to the door, and it, yes, indeed, uses the camera open CV tool. Okay, well, given that I gave you a task, and the task is part of the entity tree, and the entity tree has instances, I've implicitly just declared a task instance. So this is, at a very abstract level, a description of an actual object running in the runtime system. Okay? So we've gone all the way from some abstract specification of what the system can do to running instances. All right, but running instances aren't very interesting unless they can communicate with each other. So the other thing you got to tell me is how you're wiring together all these tasks. That looks like this. This is the data flow that I described before. All I've done is connect together in a line the processing that has to be done. This is the signature for the task, for the crop task using the face crop code, the recognize task using the face recognize code, etc. Actually has two lines here. It's been cut off. One line comes back here for the recognized ones, and then this one comes down here for the unknown ones, and then you just dump it to a terminal. And we're not restricted to pipelines. You can have arbitrary fan out, you can have arbitrary fan in. We can be, with very few restrictions, cyclic. So we don't even mind if there are cycles in this kind of graph. It doesn't. There's one edge case where that's a technical one where you have to have a particular requirement. But basically, you can have any kind of cycles that you want. Okay. Now remember, that's only one view of the data flow because each one of those tasks is attached to the entity hierarchy. So a different view, here I've thrown away the operators, which is abstract away from them. But each one of these things is connected to somewhere in this hierarchy. Okay, so the crop task turns out to be connected to the door. Crop, yes, in this particular example, crop is connected to door, heartbeat is connected to door, so it's camera. The other ones are connected to other parts of the hierarchy. Okay, so I'm building up this piece by piece abstract model of what the application is. I'm now at the last step. Given that I've described what the data flow is, the operators that are involved, this entity hierarchy of structure, I can, with a very simple algorithm, generate a node for each task instance pair. For any link in any data flow, generate an edge between those instances. I get this. So this is a running example of the system on the infrastructure that I've been given. Oh, that's nice. Remind me later. Thank you. So it's a little hard to read, but you can see the data flow showing up here. That is the heartbeat task for a particular instance, then the camera, then the crop, then the recognize, then the enrich, then the monitor. Same thing here, heartbeat, camera, crop, recognize, monitor. This path here, because these guys share instance as a parent, the messages from each of these cameras will come to this same crop task, which again flows through to the monitor. Okay. Oh, it broke. Oh, it works again. All right, so that's a summary of the whole thing. I am ready to show you a demo. All right. So this is a website which is running in the cloud. And this tool is designed to allow me to populate that application model that I described. So here I use the word ontology. In the rest of the talk, I used entity instance because when we started showing ontology to people in various academic disciplines, they started complaining. But it is actually an ontology, but nobody uses that word anymore. So task entity hierarchy is another one. Then I said that there were instances, data flows, and you saw some parameters showing up when you looked at the code. So this is the specification of the application. Then there's some other stuff you have to get to make the application work, which I'll talk about a bit later. And right now the thing's empty. And I'm a large language model fan.
Conversational interface for a security.
Oh, I didn't want that. There we go.
Application
No!
that uses cameras to monitor people.
To do it on the
volume
console.
On the console.
On the little
This thing
conference.
right here?
No, the little conference monitor by your laptop. It's probably a sound setting. The little box behind your laptop.
A little box.
The little
This thing.
display right there,
This thing.
right behind your laptop.
Mute? I could just play it.
Sure.
You get to hear my voice, I apologize.
And display a dashboard of
So what I've done here is taken a text description of my application. Actually, we took this out of the original paper that we wrote. We copied and pasted it into this form. And this is the large, and then we applied a large language model to it.
unidentified people. The developer describes the application in natural language. The conversational interface populates the application model from the description.
Yeah, I just said that. And then you go have some coffee and it generates like reams of SQL. I just find this hilarious. I don't know. I crack up every time I see this. Large language model is so much fun. This is generated, and I didn't need GPT-4 for this. This is GPT-2, okay? And I didn't do fine tuning for this. This is actually simply prompt engineering. I just provided a couple of examples. So from a half a page text description, I just populated this database. And I just raw execute this. I don't parse it or check it or anything. Obviously, for a more reliable interface, you want to do something a little smarter. But lo and behold, there are now entities which you'd expect, the relationships that we described before.
The developer
And then the populated model, okay? Now, clearly, I didn't give you the details of the infrastructure model, but it's a very similar thing, but turns out it's a lot simpler. The infrastructure description is not very complicated. You just need things like, AWS keys and login names, IP addresses. You have to know a little bit about the platform you're executing on. Does it have Python, that kind of thing. But basically, it's just a few more tables you have to fill out. So for this particular demo, we're running the building stuff in the cloud. We have a laptop, and then we have a Raspberry Pi, which we've got some cameras attached to.
populates the infrastructure model. In this example, we combine cloud services, a laptop, and a Raspberry Pi.
Probably shouldn't speak because it just duplicates it. All right.
Pre-processing of the application includes functionality injection and setup for application build.
So all I'm doing now is just running the app, right? Given that I populated the model in the infrastructure, it's now autocoder's job to generate the application. So it goes in, it looks at each, it's pretty clear what you got to do now. You got to go look at each one of those tasks, figure out what code is responsible for it, construct a little package, get that onto the right machine where it responds, and start up the associated instances.
Among other miscellaneous work. Building the application occurs in a distributed fashion depending on the location of containers.
So this is sped up because this is a prototype.
This screen recording has been sped up by a factor of 8.
8, so yeah. So it maybe we're sitting here for a minute, it was like 8 minutes. So yeah, maybe 2 coffees, something like that.
The application is started and the user visits.
So we at inject, before I only described the code, I didn't say anything about the actual operational running of the system. We inject on top of all that a complete operational running system. And now we can tell the system, we have all the controllers there, okay, start.
It's the dashboard URL. When the system executes, the monitor shows the history of values for the declared connections. Images are captured, cropped, and recognized faces are enriched with additional data.
Yeah. All right, so that's
Here
this.
we see the injected dashboard that generates a table.
All right. So because I have every touch point of every operator that's executing, I could just simply say to the system, by the way, I want you to log in a website any information that's coming out of a particular port or into a particular port. And here, all I have to do is say, okay, just stick it into tables and you visualize it. The only actual link that I have to HTML is the fact that those data objects can be rendered in HTML. So there's a little bit of code I had to write here. It's about 2 lines.
For each port that appears in the dashboard declaration.
So what you see is the heartbeats coming out of the instances. This is a captured image from a camera that's now being sent to the crop task. And because I added a little logging tab, I get to see that on the dashboard.
No user code is required for dashboards.
So then the cropping algorithm had to pick out my ugly face here. And then
For dashboards.
because that was a recognized one, I sent it off to the enrichment one. It went off, got my business key, looked myself up in the database and said, oh, by the way, this guy's got a hobby, it's fantasy football. Okay, so that was an entirely generated application.
Generated. In this section.
All right. That brings us to the end of the first part of the talk. Any questions? Yeah.
So all really interesting, but of course I immediately start thinking about evaluation and in particular, like how do you know that the generated code satisfies your requirements? How did you first of all capture the requirements? If so, then how would you test or evaluate that the software meets them?
All right, that is a really good question. And in fact, this is how I would answer it. Let's contrast that problem with what you would do today without this tool. You would write up a requirements document, right? And instead of providing it to a large language model and getting an instantiation of the application, which would allow you to inspect those individual dimensions independently, you would take that requirements, go to a particular team, hand it to that team. That requirements document would be implemented. And then you'd have some kind of audit procedure that would take that result and go back and compare it to the requirements. That audit team now has to face 2 problems. One is, does the application requirements, the underlying semantics of the application, is that correctly reflected in the code? Plus, is all the infrastructure correct, right? We've just cut that problem in half because the correctness of the infrastructure is done once. Just like in a database system, when you submit a transaction, it's the database system's responsibility to give you ACID properties. And an entire billion-dollar industry rests on the fact that when that transaction finishes, you have your ACID properties. We're saying exactly the same thing. As long as those operators, which are tiny little components, and the data flow reflects your application semantics, the rest of it we do for you. That's why it's a factor of 10 faster. That's why you only need 1/10 of the code, because 90% of the code is wrestling with monitoring and instrumentation and dashboard and all that other stuff. So right now, you can't formally check an application result. In very special cases, you can, but you really don't have a shot at it in the general case. This at least gives you a shot of saying, well, at least I partitioned the checking problem into, are the requirements reasonably reflected, and then whatever underlying demands I'm making in the infrastructure, obviously, is that correct? But of course, that only has to be solved once, not every single time I deploy an application in any distributed infrastructure, which is the case that it is today. Because that's why what we're doing has got this big leverage.
Okay, so it sounds like there's still some human element that's part of the process.
Well, yes. So the checking of the document to the code, that's still a human problem. I mean, if you want to write formal specifications and then generate this stuff, more power to you. We don't sort of care in some sense.
And I don't think you need to use formalism. Like in the example you showed, for example, if you're cropping images, you could look at error rates, you could add requirements to the graph.
At the component level. Yeah.
Right, you could see it getting really complicated as if you move from 3 entities in the graph to, I think you said you had up to like thousands?
Well, it's a prototype, but there's no conceptual limit here. So you're right. There's a question, which is, what happens when you scale up? And our solution, it's not actually a solution, but there's a constraint that I haven't talked about that helps this particular problem. And that is every one of these, modulo the parameters that you're passing, every one of these things has to operate exactly the same way. So if you, as long as every one of your, and the same way means when I deploy onto that device, it works. So I'm not worried about minor versions of the operating system changing. But clearly, if this code is written for a Raspberry Pi, but suddenly I'm using ESP32, which is the sort of the alternative, this code isn't going to work. And to do that, I would have to create a camera ESP32 operator. But then every single instance anywhere in my infrastructure that's operating that way, I'm using the same set of code and I'm manipulating that class, not individual instances. And in a major distributed application today, that's also true. Developers are manipulating sets of stuff, but they wrote all that code themselves. And it's done differently for every single organization. That's why everybody's infrastructure is different, and that's why everybody's infrastructure is a mess. Okay? I've sold this person in the audience. I don't know about anybody else, but Jonathan's like, yes. All right. So I end at 1, right? Yes.
Approximately.
I got 15 minutes. All right. So, and now I have an excuse to speed up. All right. So there's this one trick that I sort of did in there, which was like, oh, I had this arbitrary graph, but suddenly it's running in a distributed way. Okay, so how did I do that? I need some extra information. I got to know which tasks are clustered together and where they're placed. I got to know a little bit about the communication infrastructure. In the demo that you saw, we use MQTT, which is a published subscribed standard that's used everywhere in the Internet of Things world. And we also need, as I have repeatedly said, details about the particular machines, their IP addresses, et cetera. Again, we plug that into Autocoder and it generates the build, install, deploy scripts plus the control system. Well, how do I do that? Well, here's an example of my task cluster. I have a cluster called 1. I put 2 tasks together. And remember, I'm not talking about instances here. I'm talking about manipulating the task, which has the associated code and instances and parameters with it. I'm dealing at a different level of abstraction. Okay, this is a statement about the at the application level, not at the infrastructure level. Okay, and then I have a second cluster where I put everything else, and then I have to say where these clusters are located. And again, I use that entity hierarchy to talk about placement, because clustering is not the same thing as placement. I want to cluster things together so that they're co-located, but where they end up in the actual hierarchy is a separate question requiring different communication. And again, there are some technical details here. Because you're operating in a tree, you could cluster together things in a weird way that would make communication hard. If you do some of the obvious things, then you can automatically use publish subscribe. We dedicated 10 pages to this particular problem. It's a nasty little one. So let me show an example of that. Here is again the same pipeline. Here is the clustering that I imposed, right? I've said these guys are co-located. That means that this is a container. For any particular instance of this, remember there are multiple instances here, I get a process. And that means that the message from the heartbeat to the camera is no longer going through RPC or anything like that. It's a function call. I'm inside of the same space, I can simply make a function call. So we compile out everything at that point and just say, okay, I'm going to send a message to that guy, it's a function call. And then, again, there's a whole question about the threading architecture there, which we addressed, but anyways. And I do the same thing up here. The problem is, how do I communicate between these two? Because now I'm doing inter-process communication across not just a single machine, potentially across different machines, potentially across different container systems, because this is, not surprisingly, a Docker. This could be a Docker image. So what I do is I just use my own infrastructure, because now I just have an infrastructure problem. I edit, remember, not injecting code into the object itself. I'm not doing aspect-oriented programming here. I'm editing the definition of the application itself by inserting my own communication code into the pipeline. So completely orthogonally to these adapter pieces of code, depending on the number of instances I get, I will get an instance of those communication branches automatically, those communication instances automatically. Okay, and so I can inject at the application edit level remote procedure calls and message sending. Now, here's the really...
Just a clarification. So remote procedure calls is not built into Fort Alto. If you want to do it, you have to do it this way.
No, all you do is declare the port to be synchronous.
Okay.
And it gives you an RPC. And we, under the hood, we translate the RPC into message sending. We actually have the entire set of messages to give a recurrent call.
Oh, I see. This is the under the hood part.
Yeah, and the only reason we do that is because we didn't want to deal with two kinds of message communications. We wanted to only deal with one when we compile it all the way down to the bottom, but technically we could just implement RPC directly if the ports were matched. Okay, so here's the slick thing. Remember, there's only one line in the entire specification that tells me where the crop is operating. There's only one line in the entire specification that says it's in that cluster. I can go back and I can edit that cluster and say, I changed my mind. The crop is now operating in the other cluster. And then I press the button and the system completely recompiles it, and I've moved the crop code from where it was operating in the cloud to the Pi. Okay, so in a normal distributed system, this is 2 weeks of work, easily, right? Because every service that understands that the crop operator is here has to be changed. All the code, the RPC code that was being used, if you're injecting the stubs that are being used, that you have a different target, all this stuff has to be manipulated in the actual code, because today applications are built at the code level. This is exactly where mixing the application and the infrastructure kills you. And conceptually, you haven't done anything really. All you've done is optimized a little bit. Okay, and again, ranting now, that means I'm really going. Okay, so you can do this, and it's what we're doing actually in the database world isn't that unusual. All we did was push an operator from one part of the generated query tree to another part, right? This thing here, this adapter, this pair of adapters, it's called an exchange operator in distributed computing. It's essentially the same thing. Now, inside of a relational database, they got all this other stuff that they're dealing with. But the abstract idea of being able to inject an operator allows you communication between two parts of the system is exactly the same. So on the one hand, it seems radical because I'm throwing away all the infrastructure code you have to work. It doesn't seem like it would ever work. But from a database perspective, it's sort of doing what databases already do. Okay, in a sense, you have to squint. There are issues here, no doubt. But I can build basically every time I write one of those data flows, it looks like a streaming query and a streaming database. Okay. All right, last part. We've got 7 minutes. How to govern the running application. Let's suppose that we decided to change the code for the camera task. Okay, so what you'd have to do in the running system, so you don't want to take down the rest of the system, you just, I've got a firmware update or whatever kind of update. First of all, what I'm going to have to do is trace all the instances of the camera task. I need to generate a new container for each one of those. I have to build install the container communicated to the hosts. Then I have to shut down the running container because I got a new one waiting to be deployed. I've got to shut down the tasks inside of that container. Then I got to talk to the container system to say shut down. Then I've got to point to the new container and say, okay, start up. Then I've got to send a message inside of that container to start the new tasks. And then, of course, the messages that are external to all of this have been waiting. They'll flow into the new task and they'll start generating. This code we generate because this is all an infrastructure problem. And the developer or whatever other stakeholder is using a system wouldn't have to deal with this problem because we have enough information to do it ourselves. Okay, so here's the sales slide for all the PhDs in this room or future PhDs or future professors. Once you decide applications are a first order abstraction, there's all these open questions, okay? I sort of vaguely said, oh, by the way, you can do optimization, but it turns out no one's actually built such an optimizer. We've done a trivial one, but not one that I would consider industrial grade. There are all sorts of interesting questions there. And database people have been building variations of optimizers for, I don't know, 30, 40 years. You could actually analyze the performance of an application independently of running it, right? You could just simulate the inputs to a system and then track and have models for the computational costs of the things inside of it, and that would give you sort of a performance or cost estimate, right? Because the application is not independent of any of its infrastructure, okay? And then here's a fun one. Suppose you've got a bug, okay? Well, the way that you debug one of these complicated systems is you go off into your little sandbox somewhere. You get the GitHub repository of the version that's working, you copy a bunch of stuff over there, you find some logs that have been in the existing system, you copy them over, you wire up your whole new version of the system. And then a week later, you press a button and it works on your little sandbox and you can finally analyze the bug. Okay, well, we can generate that sandbox for you, right? All you need to tell us is which tasks or task instances, tasks, you want in the sandbox. And we're like, well, okay, what I'm going to do is inject the logs for all the inputs and outputs for the sub part of the graph you've shown me, run the system, create those logs, copy the whole substructure and using, again, our infrastructure deployment system to run it in your sandbox and then rerun it and compare the outputs of the local version with the outputs that you got running the production system. And in theory, they should be the same. And then when you modify that code, of course, you're now in your debugging cycle of comparing your output for the output that you got. Okay, all that work just vanished because we just leveraged the same infrastructure. Okay? And there's a bunch of other stuff here, reliability analysis, what happens if a particular component fails, all that kind of stuff. All right. Other technical benefits. We think that there's like a 90% code reduction. The new code's simpler because we stripped out all the infrastructure problems. It means you can use these AI component marketplaces. This kind of stuff's already showing up in a limited way. If you look at LangChain, they give you a framework for processing AI pipelines, and then you can sort of borrow code from other people to assemble something, but it's not nearly to the extent that we're doing. And I already showed you that conversational large language model interaction works both at the specification level, it also works at the infrastructure level, and it even works at the code level, but we're not going to do that work because there's 20 companies that are competing in the Copilot space right now. And then the data flow application space is pretty large. It's not everything. There are things that we don't do. We don't do cyber physical systems, although I would be happy to try. There's no reason why we couldn't, because we're not managing the clock. There are other issues about managing the clock for cyber physical systems. Okay, that's it. I'm on time. The main point is don't mix application code with infrastructure code, and then that gives you these three pieces. And this is the sort of the one business impact for each one of these things. That's it. Thank you. Any questions?
What's the catch?
What?
What's the catch?
The catch?
Yeah.
I don't know what you mean.
There's no catch. It's a free lunch.
It's not a free lunch. I'm sorry. I'll answer the question this way. Building autocoder itself is a real pain in the ass. I mean, Jesus, you have to really understand those tools, okay? So one of the main problems that we have, just like building a reliable database system, it's really hard. So we're solving problems that are solved over and over and over again by developers. That, I guess, would be the answer to that catch. And if you want to use a particular piece of infrastructure that we haven't figured out, you're dead in the water until we add it. So, somebody might come to us and say, oh, well, it turns out when I communicate between this task and this task, I need transactional semantics, which you can get from Kafka. Well, then we have to be able to integrate Kafka into our runtime environment, and that might take us, a couple of months. But the moment we do it, every single customer now can say, oh, this piece right here is Kafka, this piece right here. Does that answer your question?
Yeah, just to follow up on that, this seems like it's an instance of the framework story, right? You do a bunch of investment building for Alto, which is, if you squint at it the right way, it's a framework for building applications.
I'm going to push back. It's not a framework. A framework does not define an application independently of the framework. The relational model defines databases independently of any relational database system. The analogy is direct. Okay, your queries and your relations, you could put them on any different database and get approximately the same answer. That is an abstraction that exists realized in code, but it exists independently of any individual framework, right?
I see.
In the traditional sense of a framework, right?
I see. You're arguing that the model could be implemented by another.
Yes. Yeah.
Another system with the same interface.
Yeah.
Yeah. No. Okay. I get that. So let me step back a little bit,
Okay.
and maybe calling it a framework is not correct in the technical sense that you just mentioned. But I think some of the benefits you get are similar in that you're building infrastructure that pays off in a certain domain. In this case, I think a very general domain, that of data flow applications.
Right.
Yeah. And the catch is you got to match that domain.
Right, right, sure.
You know, which, you know, if it's a generic enough domain, it can be
A big enough payoff, at least
a
we
pretty
hope.
big payoff for a
Yeah,
lot of
yeah.
applications, right?
Right.
But yeah, so anyway, I mean, I'm a fan of
Frameworks?
well, frameworks and architecture, right? I think you're
Yeah, yeah,
leveraging
we're sort of
architecture
blending them. Yeah, right, right.
here.
Because again, I'm trying to think of two competing frameworks. Well, I mean, Kafka is a good example. So Kafka is, you know, a way of sending messages between processes in a data flow language that gives you certain operational guarantees about the messages that are going. And again, if you squint, it's a competitor to MQTT publish subscribe because both are publish subscribe mechanisms, but no one would ever really compare them because Kafka is really a completely different beast than some lightweight IoT protocol like MQTT. But from our point of view, it's just another infrastructure. And so, yeah, your task declaration will say, or maybe your cluster communication declaration will say, by the way, when these clusters communicate, I need transactions. And then it's like, well, okay, now we got to use something that has those requirements. So yeah. So in a sense, we are a framework, or let's say a utilizer of multiple frameworks because we compile into. No. Yeah. You had a question too.
Go ahead, sorry.
Not really related to this, but something you said in between was when you generated the SQL queries using GPT-2,
Oh, yeah.
you didn't fine tune it.
No. It's
So
all
you
prompt
said
engineering.
you only use prompt engineering. So
Yeah.
I'm just wondering how long did that prompt engineering cycle take you? Like,
Oh, how long did it take me to come up with the right prompts?
right,
To generate something that you didn't feel like you had to check before you ran.
right, and you just took the raw SQL query and ran it. So I'm very curious how long it took you.
Well, I mean, this is really technical detail, but I love this part. So let me, this is so much fun because I'm just a big fan of this stuff.
By the way, you got a
Shows
suggestion on the
Bob.
sound. You might be able to use the sound, the blue bar in the video.
Oh, there it
application.
was, sitting in front of me the whole time.
Yeah, somebody said that earlier, but then you were like, no, and I was like, oh, that probably has a reason.
Oh, sorry. I'm not good at listening.
You actually got it from one of our Zoom attendees.
There we go.
Suggesting it.
Right. So it turns out each one of these was the large language model that I built. Okay, so if you click data flow, you get a large language model whose target SQL relations are only the relations that reflect the data flow graph. And then I built a separate one for parameters and instances and the ontology. This box here, I just concatenated all the prompts.
I see.
I didn't need to engineer this part. Now, it's a demo, so to be completely frank, I did have to run it a few times and slightly edit the language.
I see.
And one thing that drove me bananas, if you look at the SQL that's generated, you have this on conflict do nothing.
Yeah.
With that, there's an integrity constraint in the underlying relations, which I probably shouldn't have put in the first place. But what'll happen is the model will redundantly generate information about the same target relation from different parts of the description. And so when it does the second insert, there will be a key violation because it's like, oh, there's already this task there. Why are you naming it again? Oh, it's the end of the world. So it turns out that the solution to that is just discard that.
I see.
Now, this is, if I was going to put on my UI hat, because I worked with those guys for a while, the first thing I'd say is, I don't know anything about user interfaces. I have enough knowledge to be ignorant about the area. This is a good first start. There are some issues here, but what I'm doing is taking a specification and giving you a formal visualization of it. Now, maybe instead of showing you tables, I should show you pretty little graphs, right? That's probably visually smarter than what I'm doing here, but you know that would take more time. And a commercial tool will do that. And obviously, you don't want to necessarily use natural language. You might want to use a drag and drop tool. It goes on and on. But I wanted to show that in theory, this happens. And when we talk to investors, this is the most important thing we show them. is because large language models are so incredibly hot now, if we can claim to be competing in that marketplace, which we are, they're suddenly interested. And sadly, that's just the facts of doing a startup. But it was an incredible, I laughed straight for an entire week. And I don't do that very often. It took me a week to build this whole thing. Every time I added something to it, it worked, and I just burst out laughing. My wife thought I was going crazy. It was just so much fun. They really are a lot of fun to use. And hallucinations aren't that big of a problem because you're not going from text to text where hallucinations are a problem. Like when I was first working with large language models, I actually asked it to do a summary of a problem the first problem I ever worked on, which is an old database problem called the view update problem. And it produced this beautiful 2-page summary with references. And the first 2 references I recognized because they were classics in the view update literature. And the third one was like, I hadn't looked at this literature in 5 years. And I'm like, wow, there's this paper in 2022 in ACM Computing Surveys. And the title of it is a survey of the view update problem by Li and Gao. I was like, I missed this paper. I'm going to love it. And of course, I go to the website. And it's not there. Right? And then I search Google. There are no 2 authors, Li and Gao, who's ever published in the database literature. It just manufactured it, right? But here I'll show you. I think it's here. Maybe it's here. No, this one turns out to be correct. I think there is a longer version of this where it uses, essentially, the model itself is providing default reasoning for where these instances show up. And it makes a mistake because I underspecified the text. I didn't say explicitly where this thing was supposed to be. And it's sort of like, based on my background knowledge of the probability of certain symbols being generated, which is like no kind of reasoning at all, I'm going to say that this goes to the door. But that's easily fixable by simple inspection, right?